From the beautiful South Studios of Way Happy, this is Mr. Meyer, 1-5 Infinite Limits. Now, I feel like this is going to feel really good because a lot of you have already been asking questions or just even discussing infinite limits. Or what do I mean by that? At some x value, the graph goes to infinity or negative infinity. And that, my friends, is the definition of a vertical asymptote. So let's just make sure we're all on the same page as we talk about this. So if you consider this graph right here, if you look at the graph, guess I'll have to fix that. If you look at the graph and the table, you will see that f of x decreases without bound as we approach 2. So here's 2. As we approach from the left side, it decreases without bound, right? Meaning it keeps decreasing forever. And it is headed to a concept that we call negative infinity. And from the right, it increases without bound. It'll just keep increasing forever. It's not bounded. It'll keep increasing forever. If we approach 1 from the right, or is that 2? Sorry, as we approach 2 from the right, and we say that that is headed to infinity, right? Because it keeps going up and up. Same thing you would get if you did this numerically on a table. If you plug in things really close to 2, you would notice as we get closer and closer to 2, these numbers are getting bigger and bigger and bigger on the right side, but they are getting smaller and smaller and smaller on the left side. Doesn't look like they're zeroing in on anything. Doesn't look like they're happy. So they're going to keep going unbounded and get larger or smaller, whichever side you're going to. So that is where we use the symbols negative infinity, infinity to say these are unbounded, right? These are unbounded. These are not real numbers. So that's the one thing you got to make sure. Infinity is a concept. It is not a number. So we can't act like it's a number. Limits are always equal to a number. So when we say limit equals infinity, we're kind of getting fuzzy here, but the limit doesn't exist, but we might talk about the limit from the left side and the limit from the right side. So be a little careful there. All right, so what can I do here? I would say that I want to do this example. Determine the limit of each function as it approaches 1 from the left and the right. So if you look at A here, whoa, who messed with my pen? If you look at A here, I don't want a highlighter. You can see that as I approach it from the left side, so as I approach from the left side of 1, this graph is going up and up and up. So I would say the limit as x approaches 1 from the negative side, then the function is headed towards infinity. Now, again, that'll drive a lot of people crazy because the limit should be equal to a number, but this is a concept, and we need some kind of concept. We need something to say it's going up and up and up forever and ever and ever. And then as I approach from the right side, I would say the limit as x approaches 1 from the positive side, the function is headed to infinity. And that's how I know that there's an asymptote, right? An asymptote meaning that the function approaches infinity at a certain given value from one side or the other, right? That's where the vertical asymptotes will lie. All right, look at the second one, B. If I do B right now, it says as we approach from the left side, I can see that this is going up and up and up without bound. So therefore, the limit as x approaches 1 from the negative side of f of x, that is headed to infinity. But if we come from the right side, it is going down and down and down. So I say the limit of f of x as x approaches 1 from the positive side is equal to negative, I almost forgot my negative, infinity. And there you have it, right? So here it is. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote. So there you go. The definition of a vertical asymptote is if when you approach that number c, whatever that x value is, if you get infinity or negative infinity for your limit, then we know it is a vertical asymptote. All right, determine the vertical asymptotes of these graphs. You guys have done this a bunch. You already know what you're looking for. Now, the one thing I would tell you is that I want to make sure that make sure it's not a hole is really what I just want to make sure you're aware of, right? So we messed a lot around with holes. It was when something factored in the top and bottom. Here it's not, right? So if you look at this graph, I know that 2 times x plus 1 cannot equal 0. So what is that? Let's move the 2 over. X plus 1 cannot equal 0. X cannot equal -1. Why? Because that's a vertical asymptote. Now, can X equal -1 in the numerator? Heck yeah. There's nothing there. So there's no X to plug in. So I know it's not a hole, right? So I can say that this is a vertical asymptote at X. Oops, where am I way up there? X equals -1. There you go. Determine all the vertical asymptotes. All right, what about this one? You're like, oh, scary, right? It's always good to factor. Can't factor the top, but the bottom I can see difference of squares. So x plus 1, x minus 1. So what do I get? I'm like, all right, x cannot equal -1 for the first one, and x cannot equal 1 for the second one. So those are my vertical asymptotes. I have 2 of them. And make sure you know they're lines, right? They're equation of line, so make sure you write the equation of a line. X, if I should be a little more careful, the way I said this part right here, right? The asymptote would be x equals 1 and x equals -1. This is kind of like a domain restriction here, where I can't have anyone, can't let it be -1 or 1. So vertical asymptote is the equation of a line, and that is the line. Uh-oh. What about C, cotangent? What the heck is cotangent? Let's see. Tangent is sine over cosine. So that means that cotangent is cosine over sine. So what does that mean? That's when sine equals 0, but cosine doesn't, because we don't want to do something else, right? So we will be in trouble when sine is equal to 0. And when is sine equal to 0? Let's see, sine, looking at my hand, that's at 0 degrees or 0 radians. And then that would happen again at pi radians, and then 2 pi radians, and then 3 pi radians. So every time the reference angle is 0, it's going to happen. So it's going to keep happening at every pi radians. So how do I say that? I say the vertical asymptote is at x equals, let's say, pi n, right? Pi radians times n. N is an integer, 0, 1, 2, 3, or -1, -2, -3. And that, my friends, is what you do for vertical asymptotes. Now, I could pause and ask a question, but maybe I will. Let's ask a question, and I'll be right back after this. All right, really good job on those ones. So let's just wrap this up real quick with theorem 1.15 that says properties of infinite limits. Now, just look at this and don't panic too much again. It's going to feel really nice. If somebody tells you, or if you know the limit of a function is infinity, and you know the limit of another function is some number, right? Then there are some neat things that you can assume about if you needed to find the limit of those things, say added or subtracted, right? If they are added or subtracted, you're going to be adding or subtracting infinity to a limit. You're still going to get infinity. That's what that one says. The product rule says that if your limit was positive and you multiply it by infinity, you still get infinity. If your limit was negative, the g of x limit was negative, and you multiply it by the other limit, which is infinity, you get negative infinity. That's all the product rule says. And then the quotient rule, probably my favorite one, says that if you take the limit of some number, and so we knew that was L, and you put it over the limit of the one that we know is infinity, infinity is a lot bigger than any number that could be in the numerator. So that's going to be 0, right? Because infinity is so big, it grows so fast, and it keeps going that there's no way the numerator could keep up with the denominator, because you're going to have some fraction like 20 over a bajillion. That's going to be 0. So the limit, if you have infinity in the denominator, then the limit is going to always be 0. And that's, I think, a nice thing to know, because it gets you thinking about numbers when the denominators are growing really, really quickly. It makes you decide that fraction's headed towards 0 if you look at their limits. All right, then I just clipped these examples out because I didn't think you guys would cry or anything. So you can see here they are, right? They said, have people do this limit right here, right? Well, they're telling me that the limit of 1 is 1, which I already knew when you head to 0. They're telling me the limit of 1 over x squared. Ooh, there's that denominator growing really, really quickly. The limit of 1 over x squared is infinity. So you have one guy that has a limit of 1. You have one guy that has a limit of infinity. And if you add those two things together, that property up there says the limit would be infinity, and I go, yay, right? Here they tell me the limit of x squared plus 1 as you approach 1 is 2 from the negative side. They tell me that cotangent, if you approach 1 from the negative side, is negative infinity. And now they ask me to divide those two. So I will have a 2 over a negative infinity. Well, remember, infinity is so big and it's in the denominator, we're going to be headed towards 0. All right, what about C? If the limit of 3, well, that's always going to be 3 no matter where you approach it from. The limit of cotangent from 0 is infinity. And if you tell me to do 3 times cotangent, that means 3 times infinity. That means you get 3 infinities. Holy macaroni, that's still our good friend infinity. And last but not least, if somebody tells you that the limit of x squared is 0, if you approach 0, that makes sense. 1 over x, there's that infinity again. The limit of 1 over x, that's going to be headed to infinity if you're at 0. Then what the heck do I know about that? Well, I know that if you do the limit of x squared plus 1 over x, then you have 0 plus infinity, negative infinity. You would still get negative infinity. That's it. Have a great day. Stay happy, and I'll see you tomorrow.